we finished up our intro to neural nets. This is real quick intro, but it's enough that you guys learned how to do neural nets. We did our homework on neural works. So they got that turned in. I want to show you, before we get into control architecture, I want to show you how you would model this physical system using neural net. That's what we're going to do today. And then we may get into controls just a little bit. I don't know how much time we have. I have a new class assignment. I want folks to do. And when we get to that point, I'll go to the blackboard to take this thing up. All right, so this is the model. The first example is a simple robot arm. A single link, just a bar that can rotate. This is an angle theta. And we'll track the position of the bar. So the equations for this are pretty simple. So for this case, we probably wouldn't use a neural net unless for some of these things. But I want to show you how we would. So for what we're doing now, we're saying theta is the input, and then x1 and x2 are the outputs. Like that. Change the zoom setting. There we go. So the equation, the block diagram, that's that. So if we wanted to use a neural net to do the same thing, one way we could do it is with a real simple neural net that looks like this. So my activation functions are sine and cosine. Here's the input. This is linear. Slope 1. And that would work, right? It's the neural net structure. We have activation functions. We have connections. We have input and output. And we looked at the equations and picked the activation functions to fit the equations. It's kind of tailor-made to the problem. But it is a neural net. Fits the structure, right? Ordinarily, we would do something more general. We'd have an input neuron and a hidden layer, maybe a couple big layers. Say tan H. And then they go to outputs. And so this would be a more general method. Where you wouldn't be stuck with that particular exact example, right? You could apply this kind of neural net to a bunch of different systems. But there's something to be learned from this, the way this is architecture. Because this says if you can pick activation functions that fit the problem, then it's a lot easier than if you just choose random activations. So if you know something about your data or the function you're trying to approximate, you pick the activation functions that fit that. Kind of like the iris stuff. We knew it was already scaled between 0 and 1. It's all positive, so we picked the sign, not the sign, the sigmoid, the positive sigmoid, and not the tanh that goes from -1 to 1. So we picked an activation function that fit the range of the data already. So that's something to be learned from the fact that you can tailor-make this thing. Now, this isn't a dynamic system. This is a static thing. Well, if we're at this angle, we're at this point position. So let's look at how we would do a dynamic system instead. So the same robot arm, but now we're going to say it's dynamic. And so the link is still at an angle theta. The theta is a function of time, and we can drive it with a torque as a function of time. If you apply a torque, the arm rotates around, it's got a moment of inertia, so if you apply the torque, it accelerates. So it's dynamics, and we still track x1, x2 as a function of time. And in fact, it's a simple rotary system, so we could model it with this differential equation. The net applied torque is the moment of inertia of the arm, rotary motion. Rotary moment of inertia, and then theta double dot is angular acceleration. So, right, that makes sense. But how do we model that with a neural net? Say, okay, we have a neural net. We're going to put in this time function, and we're going to get out time functions. But how do we put a function into a neural net? So that's what I'm going to show you next is for this kind of a dynamical system, we need to figure out what the inputs are and what the outputs are that allow us to map it. So one approach that works really well is what's called a discrete time sample. Discrete sample time system. It's an approximation, but it means you sample the function at various time steps, maybe like 0.1 seconds or 0.01 seconds. And in order to do that, we convert the differential equation from a continuous time differential equation to a discrete time sample data system. So in continuous time, let's write this as derivatives like this. This is continuous time. And then, oh, I need to finish that. That's not the whole thing. And we can make this maybe a little simpler. We'll define omega to be d theta by dt, so that angular velocity is the derivative of theta, and so the equation becomes like that. So the discrete sample data system really just means that we approximate the derivative with discrete time samples of the data. So we approximate the derivative of omega as omega as one time step ahead of where we are, and we drop back one to the time we're actually at and divide by delta t. So that's just the definition of a derivative in calculus, because if we took the limit as dt goes to 0 or delta t goes to 0, we get the derivative, right? So right now this is an approximation. We have to use small delta t's. And then omega is d theta. And so we approximate that as a derivative. And notice you can go forward in time or backward in time. We'll use this in different times. And like for omega is t plus delta t, we'll use this and then just add delta t. But either way, you take a delta t time step, essentially you're calculating the rise over the run, right? That's all you're doing to get the slope. And then you take the limit. I want to do this in a slightly different way. So then one way to model this system, the neural net, is with a state space or a state variable form. You don't necessarily need to know what state space is. Because what this means is that we'll model it in terms of omega theta, not just this equation, just in terms of theta. So we'll put both variables in there. And then theta is related to omega by this equation here. So we use the two sets of equations here. So we use this one here. And then we're going to use this one here, set equal to, we're going to plug that in over here into the differential equation. So the first equation we need is that 1 over j times okay. 1 over j times the torque is equal to that. So we use this approximation in the differential equation here. And then we're going to use the forward difference here. So I'm going to go back one time step. I'm going to go forward. We're going to say that omega of t is t plus delta t minus theta of t delta t. We'll come back to that other form of omega in a minute to do it a different way. But I wanted to start out this way first. So here we have a differential equation in terms of omega, and then the definition of theta related to omega. And really, the only step you do when you do this is you discretize all the derivatives. So we discretize d omega by dt like this, and we discretize d theta by dt like this, or with the forward step there. And then the only step left is to solve for the variable at the next time step compared to the variables at the previous time step. So let's solve this one for omega at t plus delta t. So that's this equation, and this one says theta at the next time step. And then we can look at this and we can say, okay, if I happen to know the torque currently, the current angular angle, the theta positions and omega positions at the current time, then I can jump ahead one time step to get the values of the next time step. Didn't like it. Then we can use these equations to set up a neural net. Because this says, okay, this side are the inputs, and this side are the outputs. And if we know the current values of everything, then we can predict one time step. We can have the neural net do that. So let me draw a neural net that will do this. So my inputs need to be omega at t, theta at t, and the torque at t, right? That's everything on this side. And my outputs are going to be omega the next time step and theta at the next time step. This is going to be some function that we don't know. Actually, we can go this right here. But as far as the neural net is concerned, it's some function g that takes the values of everything now and tells me what they're going to be in the future based on the dynamics. So our neural net exactly looks like that. I usually like to list the input first and then the data. And then we put maybe a hidden layer or two in here, and then the outputs would be the next time step. And there's our neural net. And we collect data from our rotary arm. We apply different torques to it. We collect the positions as a function of time. And then we train this thing to do that. So we could collect training data from that exactly that way. And in fact, we'll do this assignment with NeuralWorks, and you'll generate data by applying different torques and create data. So we would apply some torque time history And when we apply it, we would record theta, omega at that same current time. So we'd have sensors on there that would measure angular position and acceleration and the torque being applied. And we'd have, say, the torque at time step 0, theta at 0, omega 0. There's our initial conditions. And then we'd apply some torque, and the arm would start to move like this. And there we have a bunch of data that we collected from the system. Forget the neural net for now. We just collect this data. And then we look at this, and we see, well, if we're at time step 0, then those are what goes in, and then what we want to predict is the time step 1, right? So we look at our table here, and we go, okay, I need to grab this. And then where are the correct answers? They're right here. So you rearrange this data to get training pairs. And then you go forward one time step, and your inputs are this line, and your target outputs are these values. And it learns to model this system because we applied torques and we measured the outputs. And as long as it fits within the scheme of this, then we can learn to do this. So the training data would look exactly like that. So the training data would look like those values at the current time, and then we list data omega at the next time step. And that would exactly be what I just talked through over there for the first time step. These would be at 0, and then this would be at 1, and then at the next time step, these would be at 1, and these would be at 2. I guess I'm implicitly assuming that where time steps are 1 second. All right, if it's 0.1, then you just increment by 0.1 second. And to get good training on this, we would want to use a bunch of different torque time histories so that the neural net could learn how the arm behaves with different values of torque. In fact, if we're going to do negative torques, we want to do both positive and negative torques applied so that it knows a negative torque causes it to go one way and a positive torque causes it to go the other way. Otherwise, it won't learn that if you don't give it the data. And the project that we'll do, it'll be assigned in the future, is we'll apply a certain category of torque time histories, and then we'll see how well this model works for intermediate values of torque. Like we'll apply a torque of 1, 2, 3, and 4, and we'll test it at 1.5, 2.5, 3.5, and 4.5 values of torque. So I have an in-class assignment we're going to do because I've assigned a long time ago. I used to just give this to students after this lecture, and then they'd go home and not know what to do. So we're going to do it in class so that I can answer questions. But the first thing I need to do is quickly upload it to Blackboard. I forgot to do that, so give me 2 minutes to run to my office and do that. So take a break, go get a drink of water. I'm not going to hear that long. Check Facebook or Snapchat. Look at the weather.
Rain callers.
Don't wait till we reach chat.
Better than your average person by far, but
Reach chat.
I don't know.
I would not call myself good because my friends who are actually good, I would not compare myself to them.
Play video games. This is what I'm playing.
So do you go to like a skate park?
Yeah.
And you feel like
That's what I'm trying to skate is transition. When I say I'm not that good is because for creative transitions, like I could do airs and shit. I want to see.
Stay home.
But when it comes to flat ground and street, I'm just absolutely trash.
My back is right here.
Kick flips, and I can't even do a kick flip.
And you do the performance.
All top shove it's and
I
bother me
said
to
you're
do.
gonna do my performance.
I can do flips.
It's trying on a 6 feet long propeller.
A lot of people want to run outside of it.
I don't know how it, so a kickflip is you put your toe under
You don't put your toe under.
it, or you go.
So a kick flip, like let's pretend there's 2 squares of the board, and this is my toe. So you put your foot like that, and then you kick, you like shove your foot off the side, and you push it to the flip. The traditional, all you pop, and you slide your foot up and jump, and that will make like the rubber ball. I mean, one kick flip, you do the same.
She said that
Flip
other
off the
people
side,
said that they're
the
being
board
more
flips.
painful than doing
On a heel flip though. Heel flips.
Yeah,
And
and then like during when COVID started, like you know how like the yards try to like.
Most people can't control
But
it
the
easily.
people that came in were the ones that could
Congratulations.
do
You're on that, there's a no heel,
So not big.
that. That's how people they are. They're people who like
You run some
risk
more,
like going to the track.
yeah, oh, it's not the only kind of where Charles during the lecture. Texted, and he said, you know, considering it's stone courts, I'm actually mildly interested in hearing.
Like how long, and then everyone was slowed down. It's like orange Camaro.
Jim right behind you, Rob.
You back off to get back on.
My scanner won't fail me.
And then like all the accidents were close, and then I ended up on 2033. I'm like, oh.
I use Scannable.
You guys see
You're on
the 777. See that?
Walk away.
I was like crazy. You just walk out of your house.
Understand what I'm asking
What do we do? We just do it.
Just proves to show that Birdie's right in 777.
I just saved that part right away.
And then you
Found
can
it in
email
front of my house.
it, making it.
My phone is mine.
PBS.
All right, you guys on Zoom, it's on Blackboard now, it's called homework number 4. So I skipped number 3 real quick, we'll come back to it. So on here, you're going to do exactly the same process that we just did. Where you see dx2 by dt, we're definitely going to approximate that. With a triangle. The same way for everything on the left-hand side. And there's 4 variables, x1, x2, x3, x4. So then you're going to finite difference the left-hand side, all 4 equations, and then you're going to shove all of the t plus delta t's on the left side. Everything else is on the right side. And then you're going to write down the functional dependence for me. And this side is going to have x1, etc. at the next time step, and then everything else is on the right-hand side you list here. And the F and G's are functions of time. So those are the inputs to the system, and that's why the little block diagram up there says F and G go in. The differential equations are there, and then the states are x1, x2, x3, x4. Does that make sense? So you're differencing the variables, and then you're separating things out so you know what are the inputs in the network and what are the outputs. You need to draw the network, showing just like what I did there, what the inputs are and what the outputs are. You don't need to tell me how many hidden neurons you use, just draw some. Good. You're here in class, just hand me the paper back, make sure you put your name on it. If you're on Zoom, grab a piece of paper and do this at home. And then upload it to Blackboard after class. So class is done. And then I'll have it agreed. So, you guys that are on Zoom, are you clear as to what we're doing? What your job is? Assuming so, I guess they're there. And again, I'm here to answer questions. If you have questions, say something.
So you mean we're gonna move like x2 t plus delta t on one side and everything else on the other side?
All of the t plus delta t's go over here. All of the not t plus delta t's go over there.
Including the actual t, the xt, something like that.
Let's not call this f, because that confuses it with the input. Let's call this some other function. A, right? Yeah. And F and G are at the current time t. They're just like the torque that we had over there. If you need an extra sheet of paper, I've got it here. Or you can write on the back, it's your choice. I'll use a stack on the chair here.
Quick question to make sure I'm. So, like for this first one, I just plug in like this and then rearrange.
Yep. That's it.
Okay.
Then once they're all rearranged, give me just one line of that functional dependence that combines all of them together.
Okay.
And you don't have to go through like and substitute to eliminate variables on the right hand side. I don't want you to do that. You just look through the right hand side and pick X1, X2, you know, whatever's on the right hand side, then put it in the list.
Okay.
If it's already there, you don't have to list it again because you've already got it.
Mm-hmm.
I don't know. So G there.
Those are inputs to the system, just like
So
torque, T. So it's like we had torque at the current time T. So those are just at the current time T.
okay.
Yeah, I still don't understand how this works. So usually we're gonna do this one like it's not actual. This one will
No, the derivatives are the ones that will have the T plus delta T. Right, because we only have to difference the derivatives.
how about X3 and
They're
X2?
not derivatives, right? So those are at the current time. T.
So it's the actual T.
Uh-huh.
That's it.
That makes sense?
Thank you. Just,
Yeah, for the left side. Uh-huh.
Because they're in the current.
Yeah, and they're not, there's not a derivative, so you don't difference in the derivative.
So essentially, we would say basically for D, whereas the essentially more over on one side, but the
Yeah.
rest over on the other.
Right. Exactly.
Does the delta T with it? Is there just
It's just a number, it's a constant, so we want to get all of the T plus delta T's on the left, everything else is on the right. So you're isolating, the only solving you're doing is to get the stuff on the left hand side.
Good.
So like I did there, I multiplied by delta T, right? Yeah. Any other questions? I want to make sure you guys are on the right track.
one question would be like the text two there would be.
No, I don't want you to solve, yeah, you don't need to solve anything, you just shove it and then look in the list. That's all you're really doing. You guys doing it okay back here? Over there?
Try to do just like list all the outputs and then the inputs are coming.
Yeah, so you just make a list of what's there.
Almost.
Yeah.
That was right. Did I miss this?
Well, there's more stuff on this side. Yeah.
Yeah, but that's the same matters.
Well, if you look at your.
Oh,
Yeah.
it's all too easy.
Two scenarios and then this action take whatever they
And then the inputs are all of the stuff that's on the right side. Just like we did here, we didn't just have the torque as the input, we had theta and omega at the current time. You know, so I guess I did the easy one and I'm making you guys do a harder one, right? But it's the same exact process, it's just more equations. When you understand inside this bracket, there's just a list of the stuff on the right hand side, right? Yeah, separated by columns, because that's normally how you write a vector. And you just copy that list as your inputs to the on that and draw the picture. Yeah, when you're done, make sure your name's on. I'll take it here. Yeah, Doug wants you to label these with T. Yeah. Yep.
Do you do that for the F and G as well? They're all-
I'm sorry, say that again.
Are the F and G also with respect to time?
Yeah, they're time, just like the torque is a function of time. So F and G or F and G are functions of time. I understand, I'm not asking you to list all the exact stuff on the right-hand side, you're just listing the variables. I mean, you don't need delta T and all that stuff. You know, because you're gonna have all kinds of stuff, but we didn't list the delta T's, we just said, okay, there's the variable that we need to put in. The neural net figures out what it needs to multiply inside here, whether it's delta T or whatever. You don't really have to do this. I just like you to do this because it organizes from the equation. You then organize it as a functional dependence, and then you know what the inputs to your network are and what the outputs are. Yeah.
Just want to make sure. So we get all the function here, so we just,
Yeah, you just list the variables. That's it.
so this the variable.
Yeah, these are all the variables at the time t, right? But you don't need to put the delta T's and all that because that's just constants that go through.
So it's up to this one's good.
Hmm?
So up to this one's good.
Yeah, that's, make my list though, just like I said, we show the functional dependence.
I'll just like write this.
Yeah, right, a vector and then a vector on the left, but you've got the right idea.
I need to see something.
You right?
Did I say right?
No, that's exactly right. Well, I mean, you put the delta T in there. You're doing the equations, but then on the right, functional dependence of the A, you don't need to put that. You just list all the stuff you find on the left. I mean, so you're gonna take this and you multiply it with T, right? Yes, sir. And then you're just gonna shift this one over the left-hand side, and everything else go to the right. Solve and put all these terms over here.
Okay, so
So then all you have is on the left side are the deep T plus delta.
okay, so this one goes over.
Yeah, exactly.
That's so if we do that like the neural, this one is in.
Yeah, that's why I had to write the function, because it's like, okay, look at the inputs to the function, the neural net is doing the function for you.
Yeah. So we just connect like this.
Yeah.
So that's something which that is.
Yeah. And then show me what the outputs are.
I was just like x1 2 plus 2. And
And actually, once you've written that function, the neural net picture is kind of redundant, but I think it's good to say, okay, here's how we do it in neural net. See if anybody on Zoom has a question. Yeah. No, yeah. Because we're saying out here, we know the current values. Then we gotta actually go back to. Functions. Well, I mean, if you get good at it, you can look at it without the difference. And just I just crammed it all. I have one more thing I want to show you. Are you guys close to being able to wrap up? You're doing it on your tablet, so you're just going to upload it.
Yeah, you have a Blackboard link.
Yeah, it's on Blackboard.
Okay.
Unless you want to have access to a printer and you can print it out. Another question?
Yeah, I actually have a question over it.
Yeah, you just print the rest of this. What I'm saying is you have to list it twice. Next year will show up a couple of places. In the function.
So it's a PDF but only the 10th edition. And the guy wants to see that.
That's what you're going to find out. You're going to make
When
the
I ask him to say,
how many different
he didn't know.
inputs of this function. I'll give you one that was 3 of G's.
So if it has a different color edition, it will be on.
Yeah, it's still the same signal. It's still the same variable. So the neural net figures out all of the numbers. Yeah, so you just want to list everything you see on the That's it. So it's not like you're mathematically figuring out what the function is. You're just figuring out what the function is.
And these entire functions right here are just the outputs.
Yeah.
So. But. So this was. Let's go to the next side. So you have 4 different functions of those. And all okay. So that was all of the X of
No, I'm not going to give you like
so even though this is just showing them still
Well, this is the differential equation.
right? Okay.
So these are functions that go into the differential equation that solve for these.
Okay.
But when we do neural net, that's the, so that's probably the difference.
Okay, that makes more sense.
Yeah.
So one thing to point out is that if we know the initial conditions, which we usually do well, right? Then once this thing is trained, it will give us the value one time step ahead. And if we calculate those, then we can go and use those with the current torque to get the values of the next time step for the neural net after it's trained. And then we can take those and put those in with the new torque and get the values of 3. And so you can actually run this thing for over time. And if you've ever been in a class where you talk about numerical differentiation, that's all we did when we did this. We did a finite difference integration of the differential equations. But we just did that. We didn't solve them. We said, what is the structure that we need for the neural net? That's all we did.
So
Yeah.
the left-hand side, the output, the arrow is pointing to like at the top, let's say WT plus delta T, right? That's the output, and then the arrow is point to the input.
No, I think that's left over from something else I drew. These are the outputs, so this is the stuff over here, and this is the stuff over here. And this is fading. So we did it in terms of theta. This is the second derivative, second order differential equation. And so we ended up with an intermediate state variable omega that was defined to be the derivative of 1 theta. So if you do state space form where you introduce these extra variables, you end up with one input for each one. If I had a third order differential equation, I would introduce extra variables. I would end up with 3 inputs. The other way to do this is to not introduce omega at all in the final network. So what if we didn't want to have to measure omega? What if we just wanted to measure theta? Then we could still use the differential equation, but our differentiation, or a discrete time difference, would be slightly different. We could still write this like this, and then we difference this. But then we would difference the omegas. We'd use the equation for say this as well. So I'm going to take just this part and go over here. So D omega over T, you difference that thing. And then we use the formula, the definition of omega is d theta by dt And in order to make this work out right, we need to go backwards one time step. Which is totally valid, right? In the limit, you're squeezing down to where you are anyway. And then we're going to put this for each one of the omegas up here. So for omega t plus delta t, everywhere I see t, I put t plus delta t. And the delta t cancels with the minus delta t. And then for omega t, I write in this thing here. I put delta t here, and then I've got a delta t under here. What are the differences? I'm just using this formula for omega in terms of theta and sticking it in up here. And notice that now in our formula, this whole thing here is equal to 1 over j t of t. And there are no omegas. Everything's in terms of theta. But I still solve for predicting this thing at the next time step based on everything else. So according to the differential equation, this is 1 over j over t, right? So I just difference the derivative, the second derivative here. And in fact, if you've done finite difference, this is a second order difference formula. So if I solve for theta here, I don't even really need to do that, do I? You can look in your head and say, okay, I'm going to leave the theta t plus delta t over here, and I'm going to move everything else over here. And what that's going to tell me is that theta at the next time step is some function that's going to be our neural net, some time step behind, right? That's that thing. Here's theta shows up twice, and this is delta t is just a number. And so this says that I can create a neural net, a different neural net because it's a different formulation. And I can use these inputs to predict just theta one time step ahead. So I've essentially not introduced omega in the neural net. And so maybe this is more straightforward to start with. I wanted to do the other one first so we could do the assignment. So this is the other way we do it, is that for a second order differential equation, you end up with 2 past time steps. A first order differential derivative, we only need 1 past time step. If we have 2, we need 2 past time steps. So if we have 10, how many do we need? 10, right? And so we'll look at some applications where we do this kind of system modeling. We'll look at papers, and they'll just show how many past time steps they used, and we'll know immediately that they assumed it was a second order or a third order system. But fundamentally, all of these involve with just differencing the derivatives and then rearranging to figure out, well, what in the future depends upon what's current and past. And so, yeah, so I drew our neural net here, and that's all we really need for the neural net there. So I'll give you an assignment where we will do this torque problem on a robot arm, and you'll write essentially the equations, the differential equations in discrete time form, and you'll pretend that that's actually your robot. We'll put in torque into the robot, measure the values for theta and omega, and then collect them into a data set and train the neural net to do this. So that'll be coming up. So look for that. right, that's it for today.